Now we're going to finish up with Chapter 14 by looking at a couple other concepts that are related to work and energy. When we think about an object, like for instance an elevator, and an elevator is going from a bottom floor to a top floor because the engine is exerting a force upward on it. It might not just be adequate to express the work that is done on the elevator as that force moves it from the bottom floor to the top floor, because some elevators go faster than others. So how would we express, or how could we compare these two elevators and take that into account? Well, if we look at power, that was what would help us. The power is defined as the amount of work performed per unit time, or, as I like to state, I think it's more efficient to say the rate at which work is done. If we say that the amount of work is an increment of work du, then power can be expressed as du dt. But keeping in mind that we can define that increment of work as the dot product of the force with the displacement, the incremental displacement, power, which can be du dt, can also be expressed using f dr over dt, and putting these two terms together can be expressed as the dot product of force and velocity. Again, another dot product. This means that we could write the power as force dotted velocity, where it's force times velocity times the cosine of theta, meaning that only forces that have at least a component parallel to the velocity will contribute to the power. Those forces that are perpendicular to it will not, just as they didn't contribute to the work. In the MKS system of units, we actually define power in watts. But in the FPS system, the one that we use in our everyday life, it's expressed in horsepower, which actually can be converted into watts using this conversion factor. Now, sometimes we like to think about the efficiency of an engine or a machine. And the way that we talk about it is it's defined as the power input over the power output over the power input. Sometimes I like to think about it as what you get over what you gave. Where what you get is what it puts out, and what you gave is what you put in. If the amount of power that goes out is output at the same amount of time, or at the same increment of time as the power was input, you can also define the efficiency as the energy output over the energy input, because each of the power is energy over time, and then because of the ratio, the delta t's would disappear or cancel out. So as we move forward, some of our quantities some of the things we're learning about could help us solve a problem like this. Like if a roller coaster is released from the top of hill A, and if its potential energy is converted into kinetic energy, we could actually find the velocity of the roller coaster when it's at B and C, and we could also determine how fast the roller coaster has to be going in order to not leave the track. But first, we want to know, when can we talk about a potential energy that's going to be part of the conservation of energy? We start off by defining what we mean by a conservative force. So in this picture, we have a force indicated, and the lines represent that we're going to be moving from point A to point B. If we talk about the work going from A to B as the dot product of that force dotted with the displacement and going from A to B, for a conservative force, the work done in going from A to B will not depend on the path. That is, we could consider this solid line path 1 and the dotted line path 2, and we would say the work done in going from A to B, which is F dot ds, from A to B in path 1 is the same as the work done going from A to B using path 2. By definition, that is what represents a conservative force. In a sense, what we say is that the work done by the force is path independent. What is implied by that is that what only matters is where you begin and where you end. Another way to state this is that if we take a closed path, that's what this integral means, and we calculate the work done, this basically would mean we would go from A to B back to A again. The work done is 0, because of the fact that if the work only depends on the endpoints and we end where we begin, then we haven't done any work. An example of a conservative force is gravity. So let's think about the expression that we had by the work done by gravity was minus the weight times delta y, or we could say it was minus mg y2 plus mg y1. But let's think about it a little bit more visually. If I have a box with a weight mg, and it's originally at position A, and then I'm going to move it to position B, and the work done in going from A to B doesn't really matter if I go in a curved path to go from A to B, or if I take it to the side, straight up, and then over. In fact, I could draw any number of paths, and because of the expression that we see here, it only matters where I began and where I ended. It does not depend on the path. There's no way for you to discern from this expression, and I should have said the work here, sorry, should have used you. There's no way for you to discern from the expression for the work done in going from A to B what path you took, again, because it's path independent. So putting this all together, conservative forces are forces that the work done is independent of the path. The work done in taking an object from point A to point B doesn't matter how you get there. Another way to state it is that if you take a closed path, that is, if you begin where you end, the work done in that closed path is 0. So we say that the work is conserved. Conservative forces only depend on the position of the particle. They don't depend on velocity or acceleration. So if we go back to our expression that we derived in the first video, we found that the work to go from point A to point B was equal to F dot ds. Now we can also express that as minus the change in V, where V is called the potential energy function. Only conservative forces have a V associated with the force. And so we actually saw some examples of potential energy expressions, but we didn't really realize it. If we think about the work done by gravity, and going from point 1 to point 2, we find that it was minus mg y2 plus mg y1. Now we can think of that as minus the change in the potential energy due to gravity, which would be minus the difference between V2 and V1, and we actually can look through inspection, see that the potential energy due to gravity is just simply mgy, which you already knew. Similarly, we can do the same for a spring. We found the work done by a spring was minus 1/2 k s1 squared plus 1/2 k s2 squared, which is equal to minus the change in the potential energy of a spring, which would be equal to minus Vs2 minus Vs1. And again, through inspection, oh, sorry, I switched these, 2 and 1. We should say that the potential energy of a spring is 1/2 k s squared, which again is something that you probably remember. Basically, we never learned a tremendous number of potential energy functions, but when we look at a system, we can actually think about, if we're thinking from the point of view of energy, we might want to identify, is our potential energy, do we have a potential energy due to gravity in our situation, and also is there a potential energy due to the springs? And we would want to include them both if they both existed in a particular problem. Sometimes we think of potential energy is the amount of work that a conservative force will do when an object changes position. We also sometimes refer to it as the energy of position or the stored energy. And in fact, if you think about it, if the potential energy of an object due to gravity is mgy, when I hold something up in the air, I'm giving it more potential energy, and I can actually see that if I let it go and allow that potential energy change to kinetic energy. That actually happens through what we call the conservation of energy. So we're going to go back one more time to our expression for our work kinetic energy theorem and remind ourselves that we said that the work done was be equal to the change in kinetic energy, but now we just recently learned is also equal to minus the change in the potential energy. So we're going to start with that. And one of the things that we have to remember is that this will assume that only forces that are conservative are acting. This is T2 minus T1. This is minus V2 minus V1. And so if we add like terms together, that is V2 and T2 we see go on one side, and T1 and V1 go on the other side. Keep in mind that what we're saying is the kinetic energy plus the potential energy are adding up to some value that appears to remain constant. We call this the total energy. The energy total is equal to the kinetic energy plus the potential energy, and we're saying that this amount is remaining constant. That is what we mean by conservation of energy. This is a really powerful concept to use to solve a problem and can be particularly useful in something like looking at a roller coaster. So our conservation of energy is something that we're going to be able to use for some of our problems, and then use some of our other information or things that I know and solve many, many problems. And so this is really the end of chapter 14. We learned about work. We learned how work is related to change in kinetic energy. We learned how work is related to the change in potential energy. And we also learned about the conservation of energy. It's all about energy.